Welcome to Google Cloud's digital conference, Let's Talk AI. I'm Martin Gorner, developer advocate at Google Cloud. And today I'm going to be talking about TPUs, Tensor Processing Units. We have Googlers on standby to answer your questions live, so please click on the icon to your left and ask away. So let's start TPUs for developers, and this will be specifically for TensorFlow developers. TPUs are specific chips. It's an ASIC that was built by Google to accelerate the training of neural networks. This is a TPU v2 board, and now we have the third version rolling out in our data centers, and here is a screenshot. So today I want to share with you a couple of details about the hardware specifics of the TPU. Then we will talk about the software, how to adapt your models to TPUs, and finally I will show you one of my own models running on a TPU. So let's start talking about the hardware itself. This is what we call a cloud TPU. So there is the TPU board, which has 4 chips. Each chip is dual core, so that's a total of 8 TPU cores. And this board is attached through a PCI link to a host virtual machine. When you provision a cloud TPU, you get these 2 pieces together. And usually you provision a cloud TPU from your own VM, so the full picture usually looks like this. The TPU is a specific accelerator. It runs specific parts of your neural network training. So that's why there is an attached host VM, because this one will be running other things, such as, for example, your data feed code. Inside of one of those TPU cores, the part that is specific to TPUs is the matrix multiply unit. They have a hardware hardwired to perform 128 by 128 matrix multiplications. And what is important is that they perform them in mixed precision. So the input precision is bfloat16. It's a 16-bit floating point format that is slightly different from the traditional float16 format. But internally, those when you perform a matrix multiplication in bfloat16, intermediate results and accumulations happen in float32. So it's a mixed format. And of course, there is also a general purpose processor, the VPU, Vector Processing Unit, which is optimized for vector processing. The bfloat16 format is something that Google's researchers came up with. Why was that? If you look at those charts, you see all of the numbers that float32 or float16 formats can represent. And one thing to notice is that the float16 format has only 5 bits of exponent, which means that it can represent a narrower range of floating point numbers. Although it is possible to work with float16 when training neural networks, it usually means that you have to make changes to the neural network to fit this narrower range. That's why we designed bfloat16. As you can see, it's exactly float32 with the exact same range, but a reduced precision on the mantissa bits. Having the same range, usually it ends up being a drop-in replacement for your float32 inputs in matrix multiplications, especially if, as in TPUs, those matrix multiplications actually happen with float32 intermediate and final performance, precision. So maybe let's have a look at why are these matrix multiplications so important. They are at the core of neural network training. And usually they have been accelerated on GPUs. So this is how GPUs perform a matrix multiply. If you remember your calculus lessons, you remember that a matrix multiply, each resulting number is actually the dot product of a line of one of the matrices and a column of the second matrix. And a dot product is a series of multiply accumulate operations. On a GPU, you can farm out all those multiply accumulates to multiple so-called CUDA cores. And each core will be doing one or maybe several of these dot products independently. That's actually a pretty good way of doing things, and GPUs accelerate neural network training significantly. This is how matrix multiplications are organized in a TPU. The matrix multiply is implemented as a hardware unit specifically designed for matrix multiplications only. And since matrix multiplications are only made of multiply and accumulate operations, what you see here is an array of multiply accumulators connected together in a way that makes sense for matrix multiplications. So one of the matrices gets loaded into the array, and the other matrix will flow through the array. That's why this arrangement is called a systolic array, because systolic means flow in Greek, I believe. So as you see here, the numbers of the second matrix are flowing through this array. On the horizontal wires, you have the values of this matrix going up, and on the vertical wires, you have the intermediate results going to the right and being accumulated. The end result is that we can perform a matrix multiply using only tiny multiply accumulate units, which are hardwired together in the optimal way to perform matrix multiplications. But the important part is that you will typically not use those accelerators one board at a time, although you can. With 8 cores, you already get pretty significant acceleration. But we are offering these cloud TPUs in board and pod configurations. In pod configurations, you have multiple boards connected together on a high-performance computing interconnect, which makes them look as one accelerator. So you see here a picture of TPUs V2 pods that goes up to 512 cores. You can actually try it today. It's in alpha. There is a sign-up form, but you can get access. And we have announced TPU V3 pods, which are even bigger. So now let's have a look at the software side. What do you need to do to your model to adapt it to a TPU? Under the hood, the TPUs work with XLA, the linear algebra compiler, but it's under the hood. It's not typically something you are going to see. You write your model in TensorFlow, and as you know, TensorFlow produces a graph of operations representing your model. This graph is converted to XLA internal representation, and then the XLA compiler compiles that representation to TPU machine code. But that happens automatically. You just submit your TensorFlow model. Still, one limitation to be aware of is that both XLA and TPUs are optimized for vector processing. So this will actually work well for code that is data heavy. If you have code that is branch heavy, running it on a TPU is not ideal, and that's actually why there is also a CPU associated to every TPU. To port your model, the recommended way is to use the estimator interface in TensorFlow. And you will simply swap your estimator for a TPU estimator. The TPU estimator already implements all the boilerplate code needed to send your training to a TPU, which is a remote accelerator connected to your VM through the network. An estimator typically has a model function with all the layers of your model and an input function that defines the data that needs to be fed in during training. So let's have a closer look at what needs to happen to your model. First, here, for those of you who haven't seen the estimator interface yet, here is an example. Here is an estimator. When you use an estimator, the goal is usually to call estimator.train. And as you see, the estimator has been defined from a model function. So this is the model function. It contains all the layers of your model. And then when you do train, you will need data to be training on, and that is defined through an input function, which is right here. So let's see which changes I had to do to adapt this to TPUs. Well, first of all, the estimator became a TPU estimator, and I set the use TPU flag to true. This is actually quite handy because you can do the port, and by setting this flag to true or false, the same code can then run on TPUs or on GPUs. You can change your code only once and run it everywhere. The second thing is that in your data input, we recommend you to use the dataset API in TensorFlow. In regular TensorFlow, this is optional. When you work with TPUs, it's actually mandatory because some of the boilerplate code of sending data to the TPU is built into this dataset API. And one little quirk that you will have to work with is that XLA and TPUs work best when you have fixed batch sizes. So when batching your elements, please don't forget to drop the last batch because it's usually slightly different. Then, as I said, the TPU is a network-connected accelerator. So you need something to find it on the network. That's the TPU cluster resolver here. And the config is slightly different because, again, it's network attached, so it doesn't make sense to send only one iteration of the training loop to the TPU and then wait for it to call back. You want to save that network bandwidth, so you will be typically sending multiple iterations of your training loop to the TPU. The run config has been adapted to accommodate those additional configuration parameters. Finally, let's have a look at the model function. So in the model, you define your layers, and you usually choose an optimizer, and you ask this optimizer to optimize your loss. That's how you build neural network models. For TPUs, you will have to wrap your optimizer into a cross-shard optimizer, and that's the piece of code that implements the distribution of the training on the multiple TPU cores that you will be working with. 8 cores in a board and up to 512 cores in a full pod. And finally, also, the specification for metrics has changed slightly on TPUs, so you will have to refactor your metrics a little bit. The goal of all this, this API, is to allow you to run different parts of your code on different parts of the accelerator. Everything that is in your model function will actually run on the TPU. And basically anything that has a trainable variable and for which you need a gradient has to be in the model function and run on the TPU. On the other hand, your data feed or your metrics will run on the CPU, and so you have a wider range of supported TensorFlow operations that you can use in them. The TPU is still a very new architecture. The tools are evolving. The support for TensorFlow operations is improving. But today, there are still more available on CPU than on the TPU itself. The good news is that this limitation is not a limitation if you use those operations in your data feed or your metrics, only in your model code, which runs on TPU. So that's what you have to do today. And we recognize that it's work. Where we want to go is to use the new API in TensorFlow, which is called distribution strategies, and simply implement a TPU strategy. So down the line, we would like you to take your normal estimator and just reconfigure it with a TPU strategy. So this is our working goal. We will have to see how far we go from the current API to this very simple TPU strategy. But I just wanted to let you know that we are working on the porting experience to make it as seamless as possible. Here is a little list of the different code changes that I had to do when I ported my model. The first series here, as I said, it's work in progress. We are working to make this better. There are code changes, however, which are there because of system constraints. And I want to touch a little bit on those as well. The biggest among those is the fact that both XLA and the TPUs, they work best if all of your tensor sizes are fixed. Which means, as I already said, please don't forget to drop the last batch when batching your inputs. Although this is also something we are working on. Having support for variable batch sizes is kind of useful. So maybe this will be relaxed in the future. But one thing that I had to do on my image model was to make sure that TensorFlow knows the size of all the input images. So the decode function in TensorFlow reads the size from the image. So if you want, and those sizes can be different. So even if they are the same, you have to tell TensorFlow they are the same, and here is the size. One last word about Keras. Keras has an experimental TPU integration, so you can actually use Keras today, and your model will work on a TPU board. This integration doesn't yet extend to full TPU pods, but we are working on it. The good news is that in Keras, the API is simpler because in Keras we started with this simple TPU distribution strategy API. So you take your Keras model and you convert it to a TPU model applying this TPU strategy, and that is it. The good news is that when you have done all these code refactorings, and these are mostly mechanical refactorings. You take your model, you compile it, you have compiler errors, and then you try to fix those errors, refactor the code until it works on the TPU. After that, I thought that the real work would be coming, actually taking the model, thinking hard about it, and adapting it so that it takes the best advantage of the TPU hardware. It turns out the only thing you have to do is adjust your batch size. Ideally, you would use 128 batch elements per TPU core, but actually I'm getting good results already from 8 elements per TPU core. So you take your model as it is, you change your batch size, use a bigger batch size, and you're done. That's how you take advantage of all the hardware available in a TPU board or a TPU pod. To help you work with TPUs, we have also provided a couple of tools and also a whole collection of ported models. The first one is a profiler. Actually, one thing that can happen on TPUs, since this tool is, since this accelerator is so fast, is that a model that was compute bound on a GPU becomes data bound on a TPU. It cannot read the training data fast enough. And the TPU profiler will tell you that. It will tell you, well, the TPU is idling because it's waiting on data. And then you can go back to your data ingestion pipeline and try to optimize that. And there is also a TPU compatibility checker. Both of those tools analyze your model and then output their findings into TensorBoard, so you can use the TensorBoard interface and work with those new tools. Here is a list, so you have the URL github.com TensorFlow TPUs. That's a list of models that have already been ported and optimized for TPUs. So you see all the classics in there: ResNet, Inception, RetinaNet for object detection, smaller models like MobileNet, SqueezeNet, and so on. Of course, recurrent neural networks for machine translation and so on. And also, again, a generative adversarial network to generate images. So please try those models first. I have actually ported my own plane spotting model from the TensorFlow Without a PhD series of talks. And you can find it on GitHub. And actually, if you click on this link, it will show you the diff between the TPU and the non-TPU version on GitHub so that you can have an idea of what's going on. Here are the pricing ranges for cloud TPUs. So The one number to remember is $450 an hour for a V2 cloud TPU. It can be cheaper with preemptible hardware. How do you get a TPU? Well, that's the nice part. It's usually a one-liner. If you are on Compute Engine, I advise you to download this cTPU utility, or just use it from Cloud Shell. You type cTPU up, and you get one VM for you, which is one of the deep learning optimized VMs. It already has TensorFlow and CUDA and everything else installed. And you get a cloud TPU attached to it, all set up. Even port forwarding is already set up, so if you want to fire up Jupyter Lab and start working in notebooks connected to a TPU backend, that's all set up, you just have to go. On Cloud ML Engine, that's what I use mostly. Again, it's just a one-liner, scale tier equals basic TPU. That's what you specify as your hardware configuration, and you run your model. And there is a similar one-liner on Kubernetes to provision a cloud TPU for your pod. So this is my neural network R&D setup. That's how I work. TensorFlow for the models, TensorBoard for the visualizations, and ML Engine and Cloud TPUs for researching my models. At least I have found to be a lot more productive with TPUs, with models training in only 1 hour. That's really significant. So thank you today for your attention. Here is a summary of all the links that were in this presentation. You will find the presentation online as well. And this concludes our talk about tensor processing units. Thank you for joining us today. Please stay tuned for the next session, and I hope you enjoy the rest of the conference.